Welcome to today's deep dive. We're getting into something that honestly is completely invisible to most people, but it's the absolute foundation of the modern world.
Yeah, we are talking about data center infrastructure today, specifically the thermodynamics and the cooling architecture.
Right, because you think about the internet or cloud computing and you just picture data. But physically, it's just massive buildings generating an unbelievable amount of heat.
Exactly. A data center isn't a normal commercial building. When you design an office building, your priority is human comfort. When you design a data center, it's an industrial facility. It has one objective, and that is the provision of continuous 24/7 service for critical IT equipment.
And humans are actually pretty adaptable to temperature swings. Servers are not.
No, they aren't. The operational integrity of millions of dollars of hardware and the data on it relies entirely on two things: continuous power and the continuous removal of thermal energy.
Which sounds simple enough. Keep the power on, keep the servers cold.
Yeah.
But component quality alone doesn't actually guarantee that, right?
Right, because physics dictates that mechanical and electrical components will eventually fail. I don't care about the manufacturing tolerances. Every pump, every fan, every compressor has a finite mean time between failures.
So if you're aiming for absolute uptime, you can't just buy the most expensive cooling unit and hope it never breaks.
You absolutely cannot. You have to rely on redundancy. Redundancy ensures that if a specific component or even a whole supply path goes down, you don't drop the critical load.
And the industry has a very structured way of categorizing this, right? These availability tier equivalents.
Yeah, they define the topology of the infrastructure. So if we start at the bottom, you have your tier 1 equivalent.
Which is just the baseline.
Exactly. It's a simple supply path for power and cooling. No redundant components. You have one uplink. If a cooling unit fails or if you need to do planned maintenance on a switchgear, you have to shut down the IT load.
So you're taking an outage just to change a filter or service a compressor.
Yeah. And theoretically, that gives you about a 99.67% availability.
Which sounds great to a layperson, 99.67%.
It sounds great until you do the math. In a 24/7 operation, that equates to roughly 28.8 hours of downtime every single year.
Yeah, almost 29 hours offline. For a major financial institution or a cloud provider, that's catastrophic.
Which brings us to the Tier 2 equivalent. This introduces component redundancy. The standard formula here is N plus 1.
Right, so N is the baseline need plus one backup.
Exactly. Say your thermal load requires 4 cooling units to maintain the temperature. A Tier 2 facility installs 5. But, and this is the critical part, the supply path is still singular. The power and cooling distributions still flow through one single artery.
So if the pipe bursts or the main power bus fails, having an extra cooling unit doesn't help you at all.
Precisely. Your theoretical availability goes up a bit to about 99.75%, which is roughly 22 hours of downtime a year. Better, but still not fault tolerant.
So when do we get to the architecture where you can actually maintain the building without turning off the internet?
That's the Tier 3 equivalent. The defining characteristic here is concurrent maintainability.
Concurrent maintainability.
Yes. It dictates that any single component or any distribution path can be isolated and removed from service for maintenance without impacting the servers. You achieve this by having multiple supply paths, usually one active path and one passive path.
So you can seamlessly switch over.
Right. And this topology can typically tolerate around 72 hours of a municipal power outage using backup systems. Availability jumps to 99.98%.
So we went from 22 hours of downtime down to, what is that?
About 1.6 hours annually.
Okay, massive jump. But there's still one level higher.
The Tier 4 equivalent,
Right.
that's as fault tolerant.
All
The
right.
topology is described as 2N plus 1. You have 2 completely independent, simultaneously active supply paths.
So it's not active and passive. They are both running, fully compartmentalized.
Exactly. A catastrophic fire could take out one entire side of the infrastructure, and the second side just absorbs the full load without a blip. It's designed to withstand a 96-hour power outage autonomously. Availability is 99.99%, the famous 4 nines.
4 nines. And that brings the downtime down to what, minutes?
About 26 minutes a year, but it's really important to note here, when we talk about availability metrics, the frequency of the outages is just as critical as the duration.
What do you mean by that?
Well, a single uninterrupted outage lasting 60 minutes might actually be less damaging to your hardware than 60 outages lasting 1 minute each.
Because of the cycling.
Exactly. Thermal cycling and power cycling induce massive stress on silicon and mechanical joints, expanding and contracting. So the goal of all this cooling architecture isn't just to make the room cold, it's to ruthlessly stabilize the environment to prevent that cycling.
Okay, so let's get into the actual physics of how we stabilize that environment
Yeah.
and move that heat out, because it's all governed by a very specific deterministic equation, isn't it?
It is. The central equation for calculating cooling capacity on the air side is the heat balance formula. It's a linear relationship.
Let's lay it out for the listeners.
Okay, verbally, it is Q dot it equals rho O times V dot times Z dot times CP times delta T.
Right. Q dot equals rho dot times V dot times CP times delta T. Let's break those variables down because this is the key to everything. Q dot is the heat load.
Yes, Q dot is the total cooling capacity, usually measured in kilowatts. It's the rate of thermal energy being generated by the servers that we have to extract.
And rho.
Rho is the density of the air, kilograms per cubic meter. This is an environmental variable. A data center at sea level has higher air density than one in Denver, which physically changes the mass flow of your cooling medium.
Okay, and then V dot, that's the volume.
Right, V dot is the volume flow rate, cubic meters per hour. It's the actual physical amount of air the fans are pushing.
Then CP is the specific heat capacity.
Specific heat capacity of air at constant pressure. It's a physical constant. Under standard conditions, it's about 1.006 kilojoules per kilogram Kelvin. It just defines how much energy it takes to heat 1 unit of air by 1 degree.
Which leaves us with the last variable, and arguably the most important one for design, delta T.
Delta T. The temperature difference, or the temperature hub. In a data center, this is the difference between the cold air entering the front of the server, the intake, and the hot air exhausting out the back.
So if we look at that formula mathematically, for a fixed heat load, your volume flow rate and your delta T are inversely proportional.
Exactly. Cooling performance isn't just about blowing a massive volume of air. It's the product of the mass flow and the temperature spread. Let's run a calculation example.
Sure, let's say we have a fixed heat load of 100 kilowatts.
Okay, 100 kilowatts. Scenario A, we operate with a low delta T of 10 Kelvin. The air goes into the servers at 20 degrees Celsius and comes out at 30 degrees. To remove that 100 kilowatts with only a 10 Kelvin spread, the formula says you need a volume flow of about 30,000 cubic meters per hour.
30,000 cubic meters per hour. That's a lot of fan power.
It is. Now, scenario B. We optimize the airflow to get a higher delta T of 15 Kelvin. The air still enters at 20 degrees, but we let it absorb more heat, so it exhausts at 35 degrees Celsius.
Because we increase the delta T to 15 Kelvin.
Right. And to remove that same 100 kilowatts now, your required volume flow drops to about 20,000 cubic meters per hour.
Wow. So just by widening the temperature spread, you drop your required airflow by 33%.
Exactly. And fan power follows a cubic law relative to fan speed. So dropping your volume flow by a third yields massive, massive energy savings. A high delta T is the gold standard for airflow efficiency. You want to transport the maximum amount of heat using the minimum mass of air.
Okay, so we know the math of the air, but how do we actually cool that air down once it's hot? This brings us to the direct expansion cycle.
The DX cycle, yes.
Huh.
This is the thermodynamic cycle that uses a refrigerant fluid to physically pump heat from inside the server room to the outside environment.
And direct expansion just means the refrigerant evaporates directly in the coils right there in the server room unit, right? There's no middleman chilled water loop.
Correct. It's direct. The cycle has 4 main mechanical components arranged in a closed loop: the evaporator, the compressor, the condenser, and the expansion valve.
Let's follow the refrigerant through the loop. Start at the evaporator.
So the evaporator is the heat exchanger located inside the computer room, usually an in-row or a side cooler unit sitting right next to the racks. The refrigerant enters this coil as a low-pressure mixture of liquid and vapor.
And the hot air from the servers blows across that coil.
Yes. The hot return air transfers its thermal energy to the refrigerant. This causes the liquid refrigerant to boil to evaporate. It absorbs the latent heat. This evaporation happens at a very low temperature, usually between 5 and 15 degrees Celsius.
Which pulls the heat out of the air.
Exactly. It's an endothermic phase change. We call this the low pressure side of the loop. Suction pressures are typically around a 5 to 8 bar, depending on the exact refrigerant chemistry.
Okay, so now we have this warm, low-pressure gas. It leaves the evaporator and goes to the compressor.
The compressor is the heart of the system. It's the boundary between the low pressure side and the high pressure side. It performs mechanical work on that gas, violently compressing it.
And according to the ideal gas law, when you increase pressure, you increase temperature.
drastically. The compressor pushes the pressure up to maybe 15 to 25 bar. The discharge temperature of that gas coming out can easily reach 70 to 90 degrees Celsius.
90 degrees, that is incredibly hot.
It has to be hot because heat only flows from a hotter object to a colder object. To reject this heat to the outside air on a warm summer day, the refrigerant has to be significantly hotter than the ambient outdoor environment.
Which leads us to the power consumption of the compressor.
Right. The electrical draw of the compressor is directly tied to the temperature lift. The bigger the gap between your evaporation pressure and your condensation pressure, the harder the compressor has to work.
Okay, so we have this 90-degree high-pressure gas. It goes to the third component, the condenser.
The condenser is sitting outside on the roof. Fans blow the ambient outdoor air over the condenser coils. Since the refrigerant gas is much hotter than the outside air, it dumps that thermal energy into the atmosphere.
And as it loses that heat, it condenses back into a liquid.
A high-pressure liquid, yes.
Right.
But the efficiency here is at the mercy of the weather. If it's 40 degrees Celsius outside, your condensation pressure spikes. The compressor has to grind harder to overcome that pressure, which kills your energy efficiency.
Right, the coefficient of performance drops. So now we have high-pressure liquid, and we need it to be low-pressure liquid so we can boil it again.
That is the job of the fourth component, the expansion valve. The high-pressure liquid hits this restriction device, and it undergoes a massive, rapid pressure drop. It drops right back down to the low side pressure.
And a drop in pressure means a drop in temperature.
The Joule-Thomson effect, yes. The refrigerant flashes into a freezing cold, low-pressure liquid vapor mixture and loops right back into the evaporator to start all over again. The valve also regulates the superheat to make sure absolutely no unevaporated liquid hits the compressor, because liquids don't compress, it would blow the compressor apart.
So that's the thermodynamic cycle.
Mm.
But all of that is useless if the cold air doesn't actually get into the servers. Let's talk about airflow architecture, because the server rack isn't just a shelf.
No, you have to look at the server rack as an active aerodynamic component. The servers have their own internal fans, they actively pull air, they generate a pressure difference across the rack, usually between 20 and 80 pascals.
So the rack is basically an active flow channel.
Exactly. The rack's airflow demand is totally proportional to the IT load. If the processors start doing heavy computations, the servers get hot, their internal fans spin up, and the volume flow demand of the rack spikes.
So the room has to be designed to feed that demand perfectly, which is why we use aisle segregation.
Yes. You arrange the floor plan into alternating rows, cold aisles and hot aisles.
Let's define the cold aisle first. This is the supply zone.
Right. And you physically enclose it. You want to maintain the cold aisle at a positive static pressure relative to the hot aisle and the rest of the room, usually a target of +5 to +20 pascals.
Why the positive pressure?
Because air behaves like a fluid. It flows from high pressure to low pressure. A positively pressurized cold aisle forces the cold air directly into the front intakes of the servers, and it stops warm room air from infiltrating.
And then the air passes through the servers, picks up the heat, and exhausts into the hot aisle.
The hot aisle is strictly an energy collection zone. The thermal equation there is that the total heat removed has to perfectly equal the sum of the heat generated by every single rack. It is not a comfort zone for humans. It is purely a transport plenum for waste heat.
And to make this work, you have to use containment. You can't just let the air mix.
Containment is mandatory for high efficiency. You physically enclose the aisles with doors and roof panels. You are trying to eliminate mixing losses, or what we call thermodynamic short circuits.
Because if a hot aisle isn't contained, that hot exhaust air just rolls right over the top of the cabinets and gets sucked back into the cold server intakes.
Which completely degrades your delta T. By sealing the airstreams, containment guarantees that the air returning to the cooling unit is as hot as structurally possible. And going back to the heat balance formula, higher return temperature means higher delta T, which means lower fan speed and massive energy savings.
Now, a lot of these facilities use a raised floor to deliver that cold air, right?
A raised floor acts as a pressurized supply plenum. The cooling units flood the space under the floor with cold air. Then you use perforated floor tiles in the cold aisles. The positive pressure forces the air up through the perforations right in front of the server intakes.
Which is great because you can swap solid tiles for perforated ones wherever you have a really dense hot rack.
It gives you complete flexible distribution.
But all of this relies on perfect differential pressure. What happens when the pressure dynamics fail?
It leads to immediate thermal instability. The primary rule is that the cold aisle pressure has to be greater than the hot aisle pressure and greater than ambient pressure.
So what's the worst case failure mode?
The development of a negative pressure, essentially a vacuum in the cold aisle.
How does a cold aisle become a vacuum?
It happens when the volume of air being supplied by the cooling units drops below the volume of air being demanded by the server fans. The cooling airflow is less than the IT airflow demand.
So the servers are sucking harder than the room can supply.
Exactly. And because fluids move from high to low pressure, that vacuum in the cold aisle will violently suck warm air backward from the hot aisle through any tiny gap or unsealed opening in the racks. We call it recirculation.
Well, that's a disaster.
It is, because now your server intake temperature starts rising rapidly. The server's internal logic detects the heat, so it commands the internal fans to spin even faster to compensate.
Which just demands more air, pulling an even harder vacuum, sucking in even more hot air.
A textbook destabilizing positive feedback loop. Within minutes, you can have rapid overheating and thermal shutdown of the IT equipment.
But you also don't want to overcompensate and just blast the cold aisle with excessive overpressure, right?
No, excessive overpressure causes its own mechanical problems. If the pressure is too high, the containment doors literally become difficult to open or close because of the sheer force of the air pushing against them. Plus, you induce turbulent flow patterns that actually reduce the efficiency of the heat transfer.
So it is a very fine balance.
Always.
All of this mechanical work, compressors, fans, pumps, it consumes a huge amount of electricity.
Yeah.
Which brings us to the efficiency metric everyone in the industry tracks, PUE.
Power usage effectiveness. PUE is simply the ratio of the total energy consumed by the facility divided by the energy consumed strictly by the IT equipment.
So an ideal PUE would be 1.0.
Right. A PUE of 1.0 means every single watt of power entering the building is doing computational work. Nothing is wasted.
But in reality, you have lights, power distribution losses, and mainly cooling.
Cooling is by far the largest slice of the non-IT energy pie. So anything you do to optimize airflow, which reduces fan power, or optimize the thermodynamic cycle, which reduces compressor power, directly shrinks the numerator in that ratio, driving your PUE closer to 1.0.
And one of the most effective ways to crush that cooling energy cost is by implementing free cooling.
Yes. Free cooling is the use of naturally low ambient outdoor air temperatures to reject heat without turning on the mechanical compressors.
How is that actually implemented hydraulically?
Typically, you integrate a free cooling coil, which is essentially a water and glycol fluid loop-in series, with a DX evaporator coil.
So the air passes through the free cooling coil first, then the DX coil.
Exactly. And this architecture gives you 3 distinct operational modes depending on the weather outside.
Let's start with the worst case scenario, summer mode.
Summer mode is 100% mechanical cooling. The outdoor ambient temperature is higher than the server return air temperature. Thermodynamics forbids free cooling, so the system relies entirely on the mechanical compressor and the DX cycle we discussed earlier. Your energy consumption is at its absolute peak.
But then autumn comes, the temperature drops, and you enter transition mode.
Transition mode, or sliding mode. This triggers when the outside air is cooler than the return air, but it's not quite cold enough to handle the entire heat load on its own.
So it's a mix.
Right. A 3-way valve modulates the flow of the cold glycol mixture through that free cooling coil. This coil pre-cools the hot server air before it even touches the DX coil.
Which means the DX coil doesn't have to work as hard.
Exactly. The mechanical compressor is still running, but at a severely reduced capacity and a lower pressure differential. You're running fans for both systems, but the compressor energy drops significantly.
And then dead of winter.
Yeah.
Winter mode.
100% free cooling. The ambient temperature outside is so low that it can easily reject the entire heat load. The system physically switches the compressors off.
Zero compressor power.
Zero. The 3-way valve diverts the full flow to the free cooling coil. The entire thermal load of the data center is rejected to the atmosphere using just the glycol loop and the dry cooler fans outside.
The ultimate efficiency point.
It is the absolute maximum efficiency point for the infrastructure. You completely eliminate the energy-intensive vapor compression cycle.
It's just incredible to look at this whole system from a macro perspective.
Yeah.
The technical documentation really illustrates that running a data center is the ultimate system integration problem. Every single variable is rigidly coupled to the others.
It's an unbroken chain of physical dependencies. The computational load of the IT equipment dictates the exact airflow demand of the servers. That airflow demand dictates the required pressure differentials in the containment aisles.
And then the heat load and the airflow volume dictate the delta T.
Right. And that delta T combined with the outdoor ambient temperature, dictates the required vapor pressures inside the DX cooling cycle.
Which finally dictates how much power the compressors pull from the grid.
Exactly. The stability of the entire facility relies on the precise, continuous balancing of all these mass flows and energy flows. Physics permits absolutely no approximations here.
It's a closed loop of consequences. You change one parameter, and the math forces a reaction somewhere else down the line. It really makes you think about the physical footprint of the digital world. Every time you stream a video or run a database query, you are instantaneously altering the thermal aerodynamics of a room somewhere, forcing a compressor to do physical work against the atmosphere.
It's heavy industry, just invisible.
Absolutely. Well, that wraps up our deep dive into data center thermodynamics. Thanks for listening, and keep wondering about the physical machines that run our virtual lives.